Hi, everybody. In today's lecture, what I'd like to do is talk to you about how to code the electric field for a continuous charge distribution in VPython. So let me go ahead and share my screen and we'll get started. All right. So here we go, coding continuous electric fields. Now, remember that in a previous lecture, I showed you how to find a total electric field in VPython from point charges, okay? So if you have a source charge from an electric field, then what you're gonna do is you code your source charge location as a vector, you code your observation location as a vector, and then you create a vector that points from the source to the observation by subtracting these two vectors to get a displacement. Once you have that, you find the magnitude and the unit vector for that displacement vector. Then you find the magnitude of the electric field at the observation location. Once you find the electric field magnitude, then you multiply that times the unit vector that you've already found for the displacement vector. Now, if you have a lot of source charges, then what you do is you repeat that for each source and then sum up all the electric fields to find the total electric field at the point. So basically, the idea of coding a continuous charge distribution is exactly the same, except now you have a whole bunch of source charges. So you take your continuous charge distribution and you break it into little chunks. And then you find the electric field at a given point for each chunk and then sum over all of those electric field chunks to find the total electric field. And so that's what we're going to do, okay? So computationally, it's really not all that different for a continuous charge distribution than for a single point. You just got to do it again and again and again and add it all up. All right, now I highly recommend that in addition to watching this lecture, that you also read section 9 in chapter 15 of your textbook, Matter and Interactions. It goes through how to do exactly what I'm about to show you step by step, okay? And so then you'll be able to have that in writing as well. So that's really nice and really important. Now, for this week's VPython homework, I have created 2 different code for you to work from. So 2 different programs. The link is here, but I also give the link within the VPython homework, so you'll have it there as well. So here's the program I call the first one, thin rod electric field. And in this question, thin rod electric field, what I'm doing is I'm finding the electric field at a single point, single observation location for a long rod of charge. So let me just go ahead instead of working from this PowerPoint and show you the code itself. So if I pull that up, here's my code, here's thin rod electric field. So let's look at editing that code. All right, so well, maybe first I should run it for you. So here's the code. And if I zoom out, what I've done is I've taken a long rod of charge and I've broken it up into little chunks. I've visualized each one of those chunks as a red sphere. So each one of these red spheres is just meant to be a little volume element dV, okay, of a long thin rod. And then I found an observation location that's just to the right and at the middle of that long thin rod. And I've calculated what the electric field will be like at that point and visualized it as an arrow, okay? So that's what I've done. Now, that's what the code does. It's very straightforward and simple looking. So now let's look at the code itself and see what I had to do to get us there. Okay, so first of all, in the front matter of every bit of code that you have, you should define your known constants. So basically, the Coulomb constant is 8.99 times 10 to the 9th. I really should do that, okay? 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. So that's our Coulomb constant. And then what I've got here is the total charge of our long thin rod. Now, the total charge of our long thin rod is 1 nanocoulomb, which is 1 times 10 to the minus 9. Visualized here as 1 e to the minus 9. The length of our long thin rod, which I'm calling here big L, is 1 meter, okay? Now, as you saw in the code, let me go ahead and run it again. I've got 10 chunks here. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I've visualized this long thin rod as being in 10 littler chunks. Okay, so here's my length L. Here is the number of chunks. I'm calling it n equal to 10. And I could increase that if I wanted my calculation to be more accurate, right? The bigger the chunk, the less accurate your final electric field visualization will be. But I've chosen 10. And then I've said, okay, the size of each one of those chunks, which I'm going to call dy, is the length of the whole rod divided by the number of chunks, L over N. So each one, in other words, is going to be 10 centimeters. Okay, that's how big each chunk is. Now, that's the variables, the scalars that I've chosen to represent all this. Now, in order to run through each little chunk of charge, what we've done is we've created a list of point charges. So this depends upon some knowledge from that last VPython homework where we run through lists, okay? So if you didn't understand that, make sure that you get a grasp of it before you go on to try and do this homework because it uses it. We're going to create an empty list called slices, all right? Slices, the empty list will symbolize each one of the little slices of our long thin rod, okay? So remember that if you do slices and then you set that equal to the square brackets, that creates an empty list and names your list slices. Now I've got a while loop coming up, so I've got to initialize the variable for my while loop. I'm going to go ahead and call that variable within the loop I, and I'm going to set its initial value as 0. I'm going to set the initial Y location of my slice as going to be Y naught is equal to minus L over 2 plus dy over 2. So in other words here, what I'm going to do is I'm going to place my slices graphically, okay? So in order to do that, I'm going to start at the bottom of my rod and then work my way up, placing each sphere to symbolize each slice of my rod as I walk up. So in order to do that, I have to know what my bottom location is going to be. If I want my rod to run along the y-axis vertically, like I did in that figure, and I want them to run from minus L over 2 to plus L over 2, then the bottom location must be at negative L over 2 and then offset by dy over 2, which is going to be where the center of that bottom slice is, okay? So that's going to be my initial y location, minus L over 2 within a little offset so that my sphere, the bottom of my sphere sits at minus L over 2, in other words. All right, now I'm going to start my while loop. While I is less than n, okay, I'm going to create a sphere at each location. I'm going to call that sphere A, just a dummy variable name. I'm going to call it A. My sphere will be positioned on the y-axis. So the x and z positions here are 0, but my y location as given as y0 plus I times dy. So in other words, as I run through this loop, it's going to increment I, right? When it increments I, it's going to move the y position up a little bit. Okie dokie. So that's what it's going to do each time. And remember, I defined dy up here. So in other words, the first time it runs through the loop, y0 will be the same as it was outside of the loop, minus L over 2 plus dy over 2. The next time it runs through it, it's going to take that y0 and it's going to add dy. And then the next time it's going to add 2 times dy and then 3 times dy and so on and so forth until I get to the top of the rod. Now the radius of each one of these little chunks is going to be equal to dy over 2, right? And then that way it'll look like stacked spheres. I'm going to make them red. You saw that. And now I'm going to assign a new attribute, okay? And that new attribute for my object is going to be called Q, right? I'm going to call it the charge Q. And each one of those is going to have the same charge. It's going to be Q total divided by N. So in other words, each one of them will have 0.1 nanocoulombs of charge. And that breaks up the charge of the rod so that each little slice has the same amount of charge. Once I've done that, once I've created my object A, which is the sphere with all of those attributes as I listed, I want to put that sphere that I just created in my list. And to do that, I'm going to append the list. And remember from the last homework, the way to do that is to do slices, dot, append, and then put in round brackets there, A, parentheses, okay, in parentheses A. That adds the sphere that I just created to the list. Once I do that, I increment then my variable by 1, my counting variable by 1, it goes through. Okay, so it should then eventually create 10 spheres, which it does. Okay, that creates my rod. Now, at my observation location, I want to calculate my electric field. Okay, so I'm going to have a scale factor because otherwise my electric field arrow will be enormous compared to the size of my thing, and I don't want that. So I have a scale factor here. And now I'm going to calculate my electric field at the observation location. My observation location is 0.05 meters or 5 centimeters to the right of the center of my rod, which is 0.0500. Okay, so that's my vector from my observation location. I'm going to first initialize an electric field value. I'm going to start off with 0. I'm going to calculate it, but remember, sometimes you have to name your variable before you can initialize your variable before you can start. I'm going to use another while loop. I just reused I, so that means I have to initialize I again, set it equal to 0. Otherwise, if I use the same counting variable in the next loop, and I don't initialize it again, it'll start at whatever it exited at, which was probably 10. So that's silly, right? So I have to start it off at 0 again. So now while I is less than n, I assign a rate so I can visualize this. Now I've got my observation location. I defined that right here. And then I have the locations of each one of my charges. It's the positions of each one of those spheres in slice. So what I've got to do is calculate the displacement vector from the slice to the observation location. So that's R, which is R obs minus slices I dot pos. Okay. And then I'm going to calculate the unit vector associated with that position vector, which I do with R hat is equal to R divided by mag of R. Okay, I could also do that hat of R or whatever. There's a bunch of different ways. I just decided to do it this way here. Next, I'm going to calculate my electric field magnitude at that point. So it's KQ over R squared, right? So here E is equal to K times. And now the Q would be the charge of that slice. So that slices I dot Q divided by the distance squared, which would be the magnitude of R squared. And then once I've calculated my magnitude, I need to multiply that times my unit vector associated with my displacement vector so that it has a direction. So that's the times R hat. So what that means is that for each slice, I'm calculating the electric field. Okay. Now, what I'm then going to do is take whatever my electric field was before and now add on the electric field from that slice. If I do that for each slice along the way, then eventually I'll have the total electric field at that point when I exit my loop. So in other words, I've initialized my electric field vector here, my E net here. I've called it 0. But then I go through the list and calculate the electric field for each slice within the list. And each time I do that, I then update my electric field, right? My net electric field by adding on the electric field from that slice. And then when I do that, I've finished, right? When I've done that for every slice, I've finished. Then I increment my counting variable and I get out. Okay. Now, once I've done all that, I've calculated my electric field, my net electric field. Then I'm going to create an arrow to visualize that electric field. I'm going to put it, I'm going to call that arrow pointer. I'm going to put that arrow at the observation location. So that's its position attribute. I'm going to make it orange. And the axis attribute will be the magnitude and direction of the electric field at that point. So axis is equal to E net times my scale factor. Okay. Yet again, if I didn't have that scale factor, my electric field would be enormous. So let me run it. Okay, so there's my electric field vector. Let me go back though and take that scale factor out and show you what happens. See, it's just huge, right? The electric field vector is so huge, you can't see the charge anymore. So that's why I have that scale factor in there. And now it's reasonably sized, okay? So that's how to calculate the electric field for a long thin rod at a single point. Now, in your homework, the first question on your homework will be to do this again, okay? But for a different rod. So in your homework, you're going to do from chapter 15 in Matter and Interactions, you're going to do problem 64, which says to do it for a long thin rod that is, let's see, that has a net charge of -2 nanocoulombs. So you're going to have to change the net charge that the rod has. It's going to be negative. And instead of being along the y-axis, the rod is going to be on the x-axis. Okay, so you're going to have to figure out how to do that. Put it along the x-axis, not the y-axis. And you're going to have to calculate the electric field at this random point, which is -0.4, 0.3, 0.3 meters, and display that field with an arrow. Okay, and also the length of the rod is 0.5 meter. So you're going to have to go through, take my code that I just showed you, change some things around, okay? But basically you're doing kind of the same thing. So you're altering this existing code, all right? Okay, so that's that one. Now let's move on and talk about how to calculate the electric field for a continuous charge distribution at multiple points, okay? So first, let me show you what the code does. It takes that long thin rod that we had from the previous problem, the same rod, but now instead of just looking at the electric field at one observation location, this does it for multiple points, okay, as you can see here. All right, this also kind of shows you, and this is kind of neat, that the electric field, if you're not near the center of the rod, has components in the y direction as well, okay, because you're getting near the end, and so your electric field just doesn't point radially outward anymore. All right, so let's go through this code. A lot of the stuff is the same, okay? So I have this beginning part where I created the rod, that's all the same, okay? What's really changed in this code, let me zoom in a little bit, is this section right here. So what we're doing now is, in addition to creating a list for the charge itself, we also have to create a list of observation locations, okay? So I called that list observation to follow along with the text. Your Matter and Interactions text goes through multiple locations as well. So I've done that here. I've created the list. I've called it observation. Now, the y coordinate of this list is 0.4 meters. So if you remember, here's what's happening. It's choosing a single y value and it's doing a ring around that y value, okay? So I've just chosen the y value there. Now what it's going to do is it's going to go around that y value, okay, and kind of march around it in a circle. So to do that, we're changing the angle theta of the observation location, kind of like cylindrical coordinates, right? So theta here is 0, and then I'm going to increment my angle while I walk around by pi/6, which is 30 degrees. Okay, so d theta is pi/6. I'm going to walk around a circle of radius 0.15 meters. So that's 15 centimeters from my rod is my circle, okay? So how I do that, I've got a while loop. While theta is less than 2 pi, okay, I'm going to create an arrow, and I'm going to say that the position of the arrow will be at r cosine theta for the x, and then my y observation location, and then r sine theta for the z, okay? Because remember that in VPython, x runs right left, y runs up down, and then z runs in and out of the screen, okay? So my circle is in the xz plane. So that's why I have r times cosine theta for my x and r times sine theta for my z, whereas the y observation location is just, you know, constant as I walk in my circle. I make each one of those arrows orange, and just so that you can see what I'm doing within this loop, I created initially an observation location where I have a vector pointing in kind of a random direction. Okay, so there it is. Now, once I've created my observation location and visualized it with an arrow, then what I do is I add that to the list with the append command. Okay, so here I'm appending it, I'm calling it A. Okay, again, it's a dummy variable. It doesn't matter what I call it. I could call it B if you like. So there's B and there's B, right? It doesn't matter. Okay, so then I have theta is equal to theta plus d theta because I'm going to increment my angle. All right, and that creates my list of errors. So let me show you. I'm going to run it. So see how it did that? It created all these random little arrows pointing kind of up and to the right there. Now, the next bit, I'm going to use that. Now that we have our observation points defined, what we can do is with each one of those arrows that I created within the list, now I'm going to make them point the right way and have the right magnitude with the point. So to do that, I've got a loop here. And I have a scale factor yet again so that my electric field just isn't huge and I can still see my charge distribution. I did it slow so you can see how the loop goes. But of course, if you wanted to just, check your code real quick, you could up this rate, okay? So I've got nested loops here. Nested loops means that I've got a loop inside of a loop. So I have a for loop, and the for loop runs through all of my observation locations. So basically, for pointer in observation means that I've created this list called observation, and now I'm going to run through each item in that list. While I'm running through each item in that list, I'm going to call each one while I'm working on it pointer. Okay. Now I've got a nested loop, so I have to define a new initial variable for my counting. So I'm going to call that I and say it here. Just like before, I'm going to initialize my net electric field. I'm going to start it off at 0, and then I'm going to update its value as I go along. Now I have while I is less than n, okay, I calculate my position vector, my displacement vector, I'm sorry, that points from the slice to the observation location. Now remember, my observation location, I'm calling pointer. So it's pointer dot pos minus slices I dot pos. So that's where this ith slice is, right? And I'm running through all the slices with my while I is less than n bit. Then I calculate my unit vector. Then I calculate the magnitude of my electric field for each slice. And then I update my net electric field by adding on the electric field for the slice that I just calculated to the net. And then I increment my loop, okay, and I keep going. Then once I've calculated what my net electric field should be, then I visualize it with the pointer dot axis is equal to scale factor times E net. So in other words, pointer is the observation arrow that I already created up here. But what I want to do is change the direction that it points from this random direction that I assigned it up here to the correct direction for the electric field. So in order to do that, I say that the axis attribute is equal to scale factor times E net. So that's what I've done. So running it one more time, just so you can see. There it is. And I could emphasize a little bit more what I'm doing here by putting in a rate command on my while loop, right? Okay, so, oops, I'm sorry, not there. I don't want that one. I want this one to have a rate command. Tight now, pressure. Okay, so run that. See how I created the random locations of the vectors in that while loop while I'm creating my observation list, and it pointed, see the random direction, and then I updated it with the correct direction. So that's what I'm doing, okay? Now, your job for your homework, for the second question in the homework, will be to take this exact code, okay, this exact code, and instead of doing it for just one ring, do it all along the rod, okay, at 5 different rings, 5 different ring locations, equally spaced to make it simple. In order to do that, what you're going to have to do is take this section and edit it, okay? You'll have to edit this section so that you're not just going through theta, but you're also changing the position in y of your observation location. And then for each y observation location that you've got, you run through the values of theta. So you'll have nested loops for this section in order to get that done. Other than that, there shouldn't be too many changes to the code, okay? You just need to create some nested loops here, and it should be okay, all right? Okay, that's my advice on that. That's what I have to say there. I hope that makes sense, and I'll see you in class.